everyone, and welcome to the new unit on properties of waves. We're going to be talking about waves regarding all types, but we're going to be going into sound waves, light waves, and things like that. So here we go. First, of course, we want to start off with our essential questions, meaning what do we want to be able to answer at the end of this unit? What comprehension should we have? Well, our first essential question is how do matter and energy interact with when waves are generated? Number two is what are the two main types of mechanical waves? And number three, what are properties of waves? To start off, waves are a disturbance that transfer energy from place to place. Remember that energy is the ability to do work. The energy carried by a wave can lift a large ship. So, in short, whenever we have a disturbance in some sort of, whether it is physical, water or matter, so it could be water or it could be other matter, whether it is sound, whether it is light, when there's a disturbance, we know that the measurement of the waves can be determined more based upon what the waves are doing at that point. What kind of disturbance, how large or how small the disturbance, that they are transferring energy from one point of the matter to the other point. What causes waves? Waves are generated when a source of energy forces the matter in a medium, solid, liquid, or gas, to vibrate. So again, solid, liquid, and gas being our matter, and source of energy forces that matter into in a medium to vibrate, to have movement of some sort. And a vibration is repeated back and forth or up and down motion. So what is the energy source in each picture here? The energy source in this picture with the water would be the finger of this individual coming in contact with the water, which transfers energy from the person to the water. And then the second graphic, the source of energy, would be the motion of the child who is moving the string or rope up and down and transferring energy from the child's arms to the rope or string. So with mechanical waves, they only travel through a medium. Some examples would be ocean waves, which are liquid, sound waves, which travel through air or gas, and a wave can travel along a rope, which is a solid, or other types of solids, which we'll talk a little bit more about. Electromagnetic waves. Some waves can travel through empty space. These kinds of waves would be X-rays, visible light, microwaves, radio, ultraviolet waves. If you see here, this is a little scale that shows you the types of waves that you have. You go from gamma ray to X-ray to ultraviolet, and then you have this little piece here that is visible, and then past that you'd see infrared, microwave, and radio waves. Obviously, we cannot see radio, microwave, infrared, ultraviolet, X-ray, or gamma rays. What we can see are just right in this little tiny section on this line, and that's what that's light. That's where light exists in waves. So the shorter the wavelength, the higher the frequency or energy, moving down this direction here. The longer the wavelength, the lower the frequency and lower the energy, which would be closer towards radio and microwave type here. So, for a quick action, what I would like you to do is grab a blank sheet of paper or turn your notes over and see if you can complete this activity. Write down what you know about waves. How can you create a wave? What materials would you need? What is the medium your wave travels through? And what was the source of energy for your wave? So I want you to create your own wave. I don't care what kind of wave it is as long as you are able to answer these questions. So go ahead and do that and then come right back and let's pick up where we left off. There are two types of mechanical waves. Waves are classified according to how they travel through a medium. We have first transverse waves, which you can see. You have an up and down sort of movement, and then we have longitudinal waves. These waves just get closer together or further apart. Transverse waves are waves that move the medium at right angles to the direction the waves are traveling. Transverse means across. So typically your direction of medium is up and down, but the direction of the wave is moving from left to right or right to left. It's moving along a path. As a transverse wave moves in one direction, the particles of the medium move perpendicular to that direction of the wave or across it. So if you can see here with the right angle, your waves are moving across the path or the direction of the medium. Perpendicular, direction of medium, and then perpendicular to that is the direction of the wave. So some vocab words here for transverse wave would be crest, and this is where the displacement of the medium is at a maximum. So that's the top, highest, most point of the wave at each section here. And then the trough is where the displacement of the medium is at a minimum. So you see that's the lowest position. And then the rest position is where the medium shows no disturbance. So the rest position is where the medium ought to be with no wave moving it. And then the crest is the highest point for each wave. And then the trough is the lowest point for each wave. So for another quick activity here, I want you to get that same sheet of paper or turn your notes over or get a new sheet if you don't have any more room. But you are going to include all of this with your notes when you turn them in. And I want you to answer these questions here. How could you produce two different types of mechanical waves with a slinky? Sketch and label each type of wave. Describe the motion of each wave type. So go ahead and do that on your own and then come right back and we'll pick up where we left off. The second type of mechanical wave that you have are longitudinal waves. This is where the medium moves parallel to the direction the waves are traveling. So there is no perpendicular motion, it's simply the waves moving closer together or further apart along the same path. The medium moves back and forth in the same direction as the wave travels. So notice the motion of the slinky here, where you have points that are closer together and points that are further apart, but they are traveling along the same direction of the wave and of the medium. Some great vocab words that we can use here about longitudinal wave would be compression, which is where the particles are closer together, and rarefaction, which is where the particles are spread out. So you see compression here and rarefaction here. So some properties of waves and continued would be amplitude, which is the vertical distance between a peak or a valley and the resting position in a transverse wave. So if you remember, we have the crest at the top of the wave. The trough would be the very bottom of the wave, but the distance between the resting position and either the crest or the trough on each given part there is known as the amplitude. The amplitude. It's not from the crest to the trough, it's from the crest to the resting position or from the trough to the resting position. And then a measure of how, it also could be a measure of how compressed or rarefied the medium becomes in a longitudinal wave. So if you can see the distance of the wave that's closer together here in the slinky, of the medium there, and the amplitude of the medium when the wave is further apart. Both of those sections are amplitudes measured in different ways. You then have wavelength, which would be the distance between two corresponding parts of a wave. So you can measure from crest to crest or from trough to trough. This is also the distance in a longitudinal wave from compression to the next compression, or rarefaction to the next rarefaction. Frequency. Frequency is the number of complete waves or wavelengths, that pass a given point in a certain amount of time. It's the number of vibrations per second, and it's measured in the units called hertz. 1 vibration per second equals 1 hertz. So if you see this graphic here, we are measuring 1 second, and we have one complete wave that is being made. We know that because we have resting position, the wave goes up and then down, and it comes back to the resting position. So that would be one full wavelength, so that would be 1 hertz. Speed. Speed is how far the wave travels in a unit of time, or distance divided by time. The speed, wavelength, and frequency of a wave are related to each other by mathematical formulas. The unit for speed is meters per second, or m per s. So if you look here, speed equals wavelength times frequency. Frequency equals speed divided by wavelength, or wavelength equals speed divided by frequency. This might seem a little bit confusing or like a lot, but if you remember in the past, we've done the triangles with the different equations there. And so what you would have speed, or s, on the top of the triangle in that first position. And then you would have your line with your divided by symbol. And then in the left bottom corner, you would have frequency. And then you would have a multiplication symbol next to that with wavelength on that bottom right-hand corner of the triangle. So just use that same concept that we have utilized so far in this class. So here's a quick speed problem when it comes to waves. A wave on a lake has a wavelength of 0.5 meters and a frequency of 2 hertz. So 2 hertz would equal 2 waves per second, or 2 per second. To find the speed of the wave, use this formula. Speed equals wavelength times frequency. So speed would equal 0.5 meter, because that's the distance of our wavelength, multiplied by 2 hertz, or 2 waves per second. So what is 2 times 0.5? Well, it would be 1 meter per second. So now, I would like you to go ahead and do our last quick action here. This is a frequency problem, so go ahead and try to do this on your own. The speed of a wave on a rope is 50 centimeters per second, and its wavelength is 10 centimeters. What is the frequency? Write the formula, substitute, and solve the equation. Go ahead and see if you can answer these questions. Describe how matter and energy interact when waves are generated. Distinguish between the two main types of mechanical waves. And identify the properties of waves. If you could do this, then you comprehend a good bit about the properties of waves, and you are ready to move on and to study for our quiz that will be coming up next week.